Dear students, let's start this chapter, solutions and colligative properties. See, this chapter basically the extension of thermodynamics, because the what concepts all of you have developed through the thermodynamics all are applicable here in this chapter solution. But see, at your level, I'm not going to give you the more insight of thermodynamics, how thermodynamics is used here to explain the different phenomena related to the solution. But I have to use some of terms from thermodynamics, because thermodynamics controls many of your concepts of physical sciences, because all those measurements which were measured at equilibrium are said to be thermodynamically controlled properties. So here in this chapter also, all the measurements means like vapor pressure, like boiling point, like melting point, like solubility, all the parameters, all the physical terms, these terms are measured at equilibrium, so directly they are controlled by thermodynamic parameters. And you have important thermodynamic parameters like entropy, energy, and Gibbs energy, right? So in between I will use these terms, but not much use of this thermodynamics. I will I try to avoid much use of thermodynamics, right? See, what is the aim of this chapter? This is very important chapter for you. So the aim of this chapter is, first I will cover here in this chapter the concentration terms. Concentration terms, right? How to define solution, and what are different kinds of solution, and how many concentration terms we are going to use. So first I will cover that, although you have covered these terms in this terminology in class 11th stoichiometry, but here you can say a kind of revision for that. And second point, I will discuss the phase diagram, for one component, for one component system, right? And third point I will cover vapor pressure, factors affecting vapor pressure, factors affecting vapor pressure, and measurement of vapor pressure. Measurement of vapor pressure, right? And in this I will discuss the vapor pressure versus composition and vapor pressure versus temperature plots, right? And fourth part is ideal and real or non-ideal, non-ideal behavior of solution, right? And fifth point is colligative properties. Colligative properties. Colligative properties and application. And application, right? And last point be abnormal behavior of solution. See, there are many causes for the abnormal behavior, but here I will take up only when solute gets dissociated or associated. After mixing. You know, various factors affecting the behavior of any solution means various factors are responsible for abnormal behavior of solution, but here in your syllabus this is the only one point is there, that when solute gets associated or dissociated, then how behavior of solution changes. So this is the aim of this chapter. So one by one we will cover all these things. So first we will take up concentration terms, right? So see, you know, before concentration term we should know what is solution. So many of you are knowing what is the definition of solution. So I'm writing here, you can check your definition. If you have the same definition, then it's okay, and if you have some other definition, then accordingly you can correct yourself, right? See, solution is nothing but it is the homogeneous mixture of two or more than two, see here, more than two chemically different species. Chemically different. See what different technical words are scientific words used here, and you should know the meaning of all those words. See here, one term I have used here, homogeneous. So all of you should know what is the meaning of homogeneous. See, homogeneous with respect to quantity as well as quality. See, I have not written here only quantity or only quality. Homogeneous means throughout the system same property if we observe. So this is the this is known as homogeneous with respect to the quality. Means suppose that you have observed electrical conductivity or movement of ions throughout the solution. So if throughout the solution you are getting the same property, same magnitude, So you can say, okay, electrical conductivity throughout the system is same and same magnitude, so quantity is also same. Similarly, if you have dissolved this 100 gram of any solute in total volume 1 liter of the solution. So if you subdivide that solution, so equal parts, if you divide 4 in equal parts that solution, so if I mean 2.5 grams are present in equal 4 parts of the solution, then you can say, okay, this is quantitatively. So solution is the homogeneous mixture of two or more than two chemically different. This is another important word here I have used, chemically different, right? So chemically different is the mandatory situation, the mandatory condition. Otherwise you bring the H2O liquid and H2O ice, means ice and water in a beaker. Okay sir, see, this is the solution. Not like that. First thing, it is not homogeneous. If you put ice in water, this is not the homogeneous system. So this will not qualify the solution definition of solution, and also not qualify this chemically different, right? So if you have any homogeneous mixture having two or more than two components, chemically different, and the whole system is homogeneous, then the mixture is called what? Solution. So suppose that we have a component like A plus B plus C, and it is homogeneous, then it is called solution. Then it is called solution. And A and B are chemically different components. So if only two components are present, then this is called binary solution, right? If only two, then it is binary. It is binary. If you have mixed A plus B plus C, and it is homogeneous, then this is also solution. But this time this is known as what? Tertiary solution. Tertiary solution. So likewise, if 4 components are there, then quaternary and so on, right? But in many cases we will get this binary solution. This is more popular, you can say. See here, restriction I have given you in the definition, that the components should be solid or liquid or gas. Any restriction is given in the definition? If not, then there is no restriction of the phases of components, right? Means if you have taken two solids, means solid plus solid, if they form homogeneous mixture, if they are homogeneous, then this is called solution. Means two solids can also form a solution. Solution means not mandatory that liquid is there, right? So for solution, the only condition is the components should be chemically different and they are homogeneous. So example of this system is like copper plus zinc. Both are solid. Copper is solid, zinc is solid, and mixture of this, if it is homogeneous, then it is solution. And they form the homogeneous system, and they are what? Alloys. So how to make this solution? You cannot bring two pieces of copper, one of copper and one of zinc, and put together. Okay, sir, this is the solution. No, not like that. That is not solution. only physical contact is not a requirement. The requirement is they should form homogeneous mixture. They should form homogeneous mixture. So how a copper piece of copper and piece of zinc, they form homogeneous mixture? What you have to do? You have to do some physical process, physical condition you should provide. So what you have to do? You should heat both the mixture, both the pieces, melt it, mix it in a homogenizer, mix properly, and after that you should cool it, so that they can form a single piece of metal, and that piece is known as alloy. So this is the method of making the solution, right? Similarly, one solid and liquid, they also forms, if they forms homogeneous mixture, definitely that is also solution. For example, you can take sodium chloride and water. Sodium chloride is solid and water is liquid. So this is also an example of solution, because they forms homogeneous mixture. Similarly, liquid and liquid also forms homogeneous mixture. If they form homogeneous mixture, then this is called solution, and we have many example of that they are forming homogeneous mixture. For example, if you take benzene, this is liquid plus toluene. This is also liquid, and they forms homogeneous mixture, means they form solution, right? So and gas also always homogeneous, that is always solution. So gas, mixture of gas and gas is also an example of homogeneous mixture. So gas plus gas, it is homogeneous, means solution. So this is the classification and understanding of solution. Now one more thing, suppose that we have a binary solution. So in binary solution, for example, A plus B homogeneous, the component which is present in large amount is known as solvent, and the component which is present in small amount, that is known as solute. So this is the criteria of characterizing solute and solvent, right? So the component which is present in large either mass or volume or moles, right? Large amount is known as solvent, right? And one more definition is we are using for solvent. This is definition which will give you in maximum cases this will give you the correct answer, but in one case there is exception of this. So I'm giving you more precise definition of solvent. See, in any homogeneous mixture, the component, I'm giving you the more precise definition for solvent. The component which determines the final phase of final state or phase of solution is known as solvent. So in maximum cases you can determine with the help of this, but there is one case when you have to use this definition to decide whether it's solute or solvent, right? So the component which is present in large amount, that is solvent, and remember, and rest of the component and components means suppose that it is tertiary or quaternary. So solvent is only one and solute may be more than one, right? So I'm not defining here solute. If you identified solvent, except solvent, how many components are there present? All are solute. So we can define solute like this: except solvent, the component or components present in homogeneous mixture are said to be solute, right? So in this way you can determine solute and solvent. Suppose that I am taking one example here. Suppose that we have taken HCl, 3 gram HCl, and it is dissolved is mixed with 1 kilogram of water, and you know HCl is fairly soluble in water, so it makes the homogeneous mixture. Now tell me which one is the solute here and which one is the solvent, right? So the answer is solute is HCl because its quantity is less, and solvent is water, right? Because its quantity is more. And finally you tell that this HCl, what is the physical state of HCl? Anyone? What is the physical state of HCl at room temperature? The HCl is gas at room temperature. And what is the physical state of water at room temperature? The physical state of water is liquid at room temperature. So what should be the final state of solution? What is the final state of solution? What I have written here: the component which determines the final state or phase of the solution is known as solvent. So the final state of this homogeneous mixture is liquid. So this is what? Solvent, right? But you know, on the basis of this, whatsoever you determine, and on the basis of quantity is also you can determine. Now I am taking one more example to illustrate this. Suppose that we have taken HCl, 2 liters of HCl gas, it is gas, 2 liters of HCl at room temperature and pressure, and we have taken 1 liter of water, liquid. Now in this case also forms homogeneous, because here I have given you the quantity, means unit of HCl, quantity of HCl in grams. So you have very easily you have determined. Now I am giving you the quantity of HCl in terms of liters, and homogeneous mixture. And what is the final state of this mixture? Definitely it is liquid. Now see, the quantity of HCl gas is more, water liquid is quantity is less, but in this case the solvent, in this case the solvent is this, solvent is this, and solute is this. This is the exceptional case. This is the exceptional case. Right? So this is the exception. So when this exception will come? Exception will come when a gas plus liquid forms homogeneous mixture or solution. In this case, the gas is always solute and liquid is always solvent, irrespective of quantity. Because in this case, we are using which definition? This definition, but this definition, visualization of this definition is a little bit difficult. So this definition all of you are using many times, but this is not, this will not give you the, always give you the correct answer. But this definition is ambiguously correct, right? Always give you the correct result. So you can prepare this as an exception, that when a gas is mixed with a solid or gas is mixed with a liquid and making a homogeneous mixture, then gas is always solute and liquid is always solvent. Because ultimately liquid or solid will determine the final state, gas will not determine the final state of your solution, right? So this is the definition of what solution, how solution is defined, how many types of solution we may have, and what is the classification of solute and solvent, how to determine solute and solvent, right? Now come to the next point, that is concentration terms. Concentration terms, right? So concentration terms, these concentration terms, what are these concentration terms? The concentration terms are the technical terms, or you can say formulas used to express the quantity of, relative quantity of solute versus solvent. So concentration terms are the technical terms. Concentration terms are the technical terms used to express the quantity relative quantity of solute and solvent together. Right? So these are the terms which enables us to express the quantity relative quantity of solute versus solvent. Sometime we use this actual value, and sometime it is calculated value, but no problem. So these are the concentration terms. So I am considering one binary mixture A and B, homogeneous mixture means solution. I am taking this, where B is solute, and this is solvent. A is solvent and B is solute. I am taking this as an example, standard, right? So whenever B subscript anywhere I am using, means I am talking about the solute, and when A, that is solvent. So see, the first concentration term I am taking, that is the mass percent. Mass percent. Mass percent. See, percent. How to express the percentage? All of you are knowing that percentage is nothing but the simple definition of percentage is the fraction. Fraction per 100 part. That is called percentage. So this is purely mathematical terms. If you are not getting what is the meaning of fraction, obviously for you it is very difficult to understand mass percent. Fraction. How to determine the fraction? What is the necessary condition for the determination of fraction or calculation of fraction? You know, for the fraction, for the calculation of fraction, all the components must have same unit. Means suppose that you are going to calculate the mass percent or mass fraction. So whatever components given in the mixture, means what solute and solvent both must have the same unit, grams, then or kilograms or milligrams, whatever, but must have same unit. Then you will get what? Mass percent. So percent is basically fraction per 100 parts. Similarly here, mass fraction per 100 part is called what? Mass percent. So obviously now all of you are grown up in class 12. All of you are knowing how to calculate the fraction, right? So mass percent is the mass fraction per 100 part of solution is called mass percent. Mass percent, right? So this is the very simple and very precise definition of mass percent. So I am considering this AB a solution. So mass percent of B is equal to mass of B over mass of A plus mass of B. This is the mass fraction into 100. So this is the mass percent of B. Similarly, mass percent, we do not have any notation for this, so you have to write like this: mass percent of A is equal to WA over WA plus WB into 100, right? And this is also written as like this: W by W, right? So you can write here mass percent of B solute plus mass percent of A means solvent is equal to 100 always. So this is always true. So in a binary mixture, if you have a percentage of one component, so you can very easily determine the percentage of other component, because you know that sum of mass percent is always equal to 100. Similarly, if your solution have three components, four components, so you can write that mass percent of I component, this is equal to 100, right? So sum of mass percents is always equal to 100. This is always true, right? So this is the simple formula for the calculation of mass percent, and here in the denominator you can take total mass of the solution. That is also true, and all of you are knowing that in the mixing there is no loss of the quantity, right? So the total mass of solution is always equal to the mass of A plus mass of B. Now see, another percent relation is mass to volume relation. So mass volume W by V percentage, right? So in this case, the mass of solute you have to take in grams, and the volume of solution basically you have to take in what, volume, in terms of volume, means liter or ml whatsoever. So how to define this? The mass of solute present per 100 ml of solution, per 100 ml of solution. So you can write the mass volume percent of B is equal to mass of B divided by volume of solution in ml into 100. So you can make this formula. Right? Now the next one is the volume percent. volume percent. This is called V by V. V by V. So this can be defined as the volume fraction per 100 part of solution is known as volume percent. Right? So volume percent of B means solute is equal to volume of B by total volume of solution into 100. Similarly, volume percent of A is equal to volume of A divided by total volume of solution into 100. Right? So you have two different formula, but if you see carefully, then there is some difference with respect to the mass percent here. There is some difference. What difference? See here, I have not written here total volume of, in place of total volume of solution, volume of A plus volume of B, as I have written here mass of A plus mass of B. See, there is a point. I cannot write here VA plus VB because we know as a chemist, chemistry people, we know that the total volume of any solution, solution may or may not equal to VA plus VB. Right? So total volume of solution, suppose that you are mixing two liquids. Basically this term is used for two liquids, mixing of two liquids. Suppose that if you are mixing two liquids, so it is not necessary that the total volume V total is equal to VA plus VB, but it is also possible that V total is not equal to VA plus VB. This is very, very important generalization for you people, because in this chapter you will encounter with this type of problem, right? So it is not mandatory that always we are getting, suppose that you are mixing 50 ml of ethyl alcohol and 50 ml of water, you know 50 plus 50 is equal to 100, but it is not equal to 100. So you have one example, very well known example, that 50 ml of water plus 50 ml of ethyl alcohol, C2H5OH. This is equal to, you know, if you mix these two, you will get 98 ml. 98 ml of mixture. You won't get 100 ml. Never get 100 ml. Right? So 50 ml, if you mix 50 ml of water and 50 ml of ethyl alcohol, so you will get 98 ml. So in this formula, you have to careful total volume of solution. You have to put not the volume of A plus volume of B, right? So what the consequence of this? The consequence of this is that the volume percent, sum of volume percent may or may not be equal to 100. So the sum of volume percent, sigma of volume percent, of I components may or may not, equal to 100%, right? This is the consequence of this. As you have written here that mass percent of A and B, that is always equal to 100, but here you cannot say that the sum of sigma of volume percent of ith component may or may not be equal to 100%. For example, if you take this example, so what you get, see here from this example, what is the volume percent of ethyl alcohol? Volume percent of C2H5OH. So volume percent of C2H5OH is equal to 50 by 98 into 100. So 50 by 98 into 100. So what you get? 50 divided by 98, you will get 51.0. 51.0%. Similarly, volume percent of water is also equal to 50 by 98. So this is equal to 51.0%. So what is the volume percent? Sum of volume percent is equal to 51 plus 51, so this is equal to 102%. So percentage may be greater than 100, but they are very special cases in which on mixing two or more than two components, if there is a expansion in volume, then you will get the percentage less than 100, and if there is a contraction in volume, then the percentage is greater than 100, right? So this is all about percentage concentration term the first concentration term, the percentage concentration term. Now it is complete. All types of percent concentration term. So we have three types of percent concentration term. One is W by W, second one is W by V. W by V is very not much popular, and third one is V by V, right? So this is all about the percent concentration terms, right?